So we explore here whether the integers with respect to multiplication could form a group. Now the first question to ask is, what could the identity element be? And the identity element is an element, let's call it E, such that, and I will use the abbreviation ST for such that, M times E is E times M is M for all integers M. And now we know the integers rather well, and we rely on that knowledge to realize that the only possible choice is that only possibility is that E equals 1. There is no other integer that would satisfy any integer times E equals E times that integer equals that integer itself. Now, what about inverses? Okay, so given an integer A, the inverse of A is an integer, let's call it B, such that A times B equals B times A equals E. And in this particular case, we have decided that E can only be 1. And so we're asking that given an integer A, there has to be another integer B such that A times B is B times A equals 1. Now let's take A equals 2, for example. They ought to be an integer. So let me ask this as a question. Does there exist an integer M, let's say, or B, whatever you want to call it, such that 2 times M is M times 2 equals 1? And the answer very clearly is no. So what we find from this is that Z with respect to multiplication is not a group. Now, a little remark is in order regarding the line above. You might ask yourself, yes, given A equals 2, for instance, there is certainly no integer M such that 2 times M equals M times 2 equals 1. But if we take B equals a half, then indeed, yes, 2 times a half equals a half times a 2 equals a 1. And you may ask yourself, what's going on here? Does this contradict in any sense our statement that Z with respect to multiplication is not a group? And the answer is there's no contradiction. And this is something you want to get used to. You see, you have Z inside this circle, for instance, and you have here the rationals, which we denote as a Q out there. It's a strictly bigger circle. And you have 2 in here, and half is outside of this circle. And so, for instance, this 2 that we're interested in, the quote-unquote inverse we have found is outside this circle that 2 lives in. What we're really interested in when we're asking if Z, which is just this small portion here, is a group with respect to multiplication, we want all our inverses of elements in Z to live inside that circle itself. It's no use pointing to something that lives outside and saying, oh, there's an inverse out there, so therefore the smaller circle must form a group. So that's something you have to keep in mind. We are very restrictive when we ask our question. Now, of course, there is then a corresponding question, and that question is, given that, for instance, we have found that something like 2 has an inverse here, and you can play the same game yourself. For example, 5 there has an inverse 1 over 5 out there. That might lead you to think that For instance, Q with respect to multiplication is a group. And we can ask ourselves the corresponding question, is that correct or not? And the answer is no. I'll let you think about that for yourself. Why is that not a group? But a very broad, a very pointed actually hint is that study the element 0. And let me leave you then with a corresponding question that comes from the hint. Is Q without the element 0, that's how you read that, Q without the element 0 with respect to multiplication, is that a group? And I leave you to ponder that. I will even tell you the answer. The answer is yes, but think about it and try to prove it for yourself.